ओके, नमस्कार. तर आज आपण सिस्टम ऑफ फर्स्ट ऑर्डर लिनियर डिफरेंशियल इक्वेशन जो की युनिट सेकंड पेपर थर्ड कुठल्या वर्गाचा आहे B.Sc सेकंड सेम थर्ड. ठीक आहे, त्याच्यामधला युनिट सेकंड आपण सिस्टम ऑफ फर्स्ट ऑर्डर लिनियर डिफरेंशियल इक्वेशन सुरू करणार आहोत. याच्या अगोदर आपण मागच्या युनिटमध्ये हायर ऑर्डर होमोजेनियस डिफरेंशियल इक्वेशन विथ कॉन्स्टंट कोएफिशियंट, मेथड ऑफ व्हेरिएशन पॅरामीटर, कॉम्प्लिमेंटरी फंक्शन, जनरल सोल्युशन म्हणजे काय, कंप्लीट सोल्युशन म्हणजे काय, ह्या सगळ्या गोष्टी बघितलेल्या आहेत. तर आज आपण सिस्टम ऑफ फर्स्ट ऑर्डर लिनियर डिफरेंशियल इक्वेशन बघणार आहोत. जनरल फॉर्म काय आहे त्याचा? द जनरल फॉर्म इज द सिस्टम म्हणजे एकापेक्षा जास्त इक्वेशन जेव्हा एखाद्या एक्सप्रेशनमध्ये येतात तेव्हा त्याला सिस्टम म्हणतात. द सिस्टम ऑफ लिनियर इक्वेशन्स, द सिस्टम ऑफ लिनियर इक्वेशन्स dx by dt is equal to capital F of x comma y comma t and dy by dt is some function g of x comma y comma t, where f and g are the linear functions, of the variables x, y and t. This is called as a system of linear equations in the variable x, y and t, where x and y are the dependent variable and t is my independent variable. Now we have an existence. Now first of all, when this system of equation has a solution or not, there are many examples we can produce with the help of this expression. For example, we have a system of equation dx by dt is equal to y, dy by dt is equal to x. This is simply a system of equation. We can design many more example like dx by dt is equal to 4x plus 7y, dx by dt is equal to 4x plus 7y and dy by dt is equal to 6x minus 3y. Or we can introduce here plus t plus 2t. These are the only functions of x, y and t, So this is another example of a system of first order linear differential equation. Here order is mandatory, that it is a first order and it is a linear differential equation. Existence and uniqueness for solution to linear system. Consider the system of equations. Dx by dt is equal to f of x comma y comma t and dy by dt is equal to g of x comma y comma t are the linear differential equations, are the system is an system of linear differential equations. Obviously here f and g are the linear equations. Now suppose t0 belongs to the closed interval ab. Here f and g are continuous and linear. F and G are continuous and linear. More precisely, we can write it as a f of x comma t can be written in the form of like a1 of tx plus b1 ty plus f1 t, or here we can write this as a2 t x plus b2 ty plus f2, where this a1 b1 f1 a2 b2 f2 are continuous functions for all t belongs to the closed interval ab, where all these functions are the continuous and defined for all the points belongs to the closed interval ab. That is the continuous function defined on a bounded closed interval ab. Now suppose t0 belongs to closed interval ab, be a fixed point and x0 and y0 be any two fixed real numbers, or any two fixed real numbers, then the above system of equations has a unique solution x is equal to x of t and y is equal to y of t, valid through closed interval ab, such that x of t0 is equal to x0 and y of t0 is equal to y0. This is the existence and uniqueness for the solution of this linear system of differential equation. This has a proof, but the proof for this theorem is beyond the scope of syllabus, because this is not included in the syllabus. So we have to keep in mind only the statement of this theorem, that whenever this system of equation has a solution, then it has a unique solution which satisfies this initial condition. म्हणजे ही इनिशियल कंडिशन सॅटिस्फाय करणारं ह्या डिफरन्शियल इक्वेशनला एकच सोल्युशन एक्झिस्ट असणार आहे, आणि ते एक्झिस्ट असणार आहे. Now next theorem we have, let t belongs to closed interval ab. Suppose x is equal to x1 of t, y is equal to y1 of t, and x is equal to x2 of t, y is equal to y2 of t be two solutions to the homogeneous system of equations, dx by dt is equal to a1 of t plus b1 of t x, dy by dt is equal to a2 of t x plus b2 of t y. Then x of t is equal to c1 x1 of t plus c2 x2 of t, y of t is equal to c1 y1 of t plus c2 y2 of t is also a solution is also a solution to the above homogeneous system of equations for t belongs to the closed interval AB. Proof. What we have given that? We have given that the two solutions x is equal to x1 of t, y is equal to y1 of t is one solution. Another solution x is equal to x2 of t, y is equal to y2 of t is these are the two solutions for the system of equation, for the system of homogeneous system of equation dx by dt is equal to a1 of t x plus b1 of t y, dy by dt is equal to a2 of tx plus b2 of ty. That is, these are the, suppose this is a, this is b, a and b are the two solutions for this system of equations. Then to prove that x of t is equal to c1 x1 of t plus c2 x2 of t, y of t is equal to c1 y1 of t plus c2 y2 of t. Then these are the two solutions for the given system of equations. Now from A and C, we have, what is A? A is the solution for this system of equation. A is the solution for this system of equation. It means that A must satisfy C. So we have dx1 by dt is equal to a1 of t into x1 plus b1 of t into y1. dy1 by dt is equal to a2 of t into x1 plus b2 of t into y1. Suppose this is equation D. Also from B and C we have, because B is the solution of C, so B must satisfy C. dx2 by dt is equal to a1 of t into x2 plus b1 of t into y2. dy2 by dt is equal to a1 of t a2 of t x2 plus b2 of t y2. Suppose this is equation E. Suppose this is an equation E. Now from equation D and E we have, from equation D and E we have c1 into dx1 by dt plus c2 into dx2 by dt is equal to c1 a1 of t x1 plus c2 b1 of t into y1 into c1 plus c2 into a1 of t into x2 plus c2 b1 of t into y2. This implies that d by dt of c1 x1 plus c2 x2 is equal to a1 of t into c1 x1 plus c2 x2 plus b1 of t into c1 y1 plus c2 y2. Suppose this is equation f. Suppose this is equation f. Similarly, we have c1 dy1 of t plus c2 dy2 by dt is equal to c1 a2 of t into x1 plus c1 b2 of t into y2 plus c2 a2 of t into x2 plus c2 b2 of t into y2. And if we solve this, we get d by dt c1 y1 plus c2 y2 is equal to c1 into a2 of t x1 plus a2 of t into x2 plus c2 here we have a2 of t into c1 x1 plus c2 x2 plus b2 of t into c2 y2 plus c1 y2 plus c2 y2. Suppose this is equation G. Hence from f and g we have x is equal to c1 x1 plus c2 x2 and y is equal to c1 y1 plus c2 y2 is also a solution of C. Hence the proof. Now next we have definition of Wronskian of solution of linear system. Let x is equal to x1 of t and y is equal to y1 of t and x is equal to x2 of t, y is equal to y2 of t be solution of linear system, with the solution of linear system dx by dt is equal to a1 of tx plus b1 of ty, dy by dt is equal to a2 of tx plus b2 of ty. Then its Wronskian is given by w of t is equal to x1 of t, x2 of t, y1 of t, y2 of t. That is, if we solve this, we get x1 of t into y2 of t minus x2 of t into y1 of t. That is determinant of this is nothing but the cross product, this into this minus this into this. Now we have remark if W of t is the Wronskian, W of t is the Wronskian of two solutions x is equal to x1 of t, y is equal to y1 of t, and x is equal to x2 of t, y is equal to y2 of t, to the homogeneous system 1. Which one is the one? Suppose this is our homogeneous system of linear equations. Suppose this is 1. Of the homogeneous system 1 of differential equations, then either W of t is identically 0 or W of t is never 0. W of t is never 0. So Wronskian is either identically 0 or it is never 0. If we summarize the proof of this, we have the given system of equation 1. We have this is the given system of equation. This is the given system of equation, and these are the solutions of this system of equation. It means that this system of equation satisfies this. If we substitute this and do some mathematical calculations, we get Wronskian is equal to c into e to the power integration a1 of t plus b2 of t dt. This is the value of integration. This is the value of Wronskian with the help of given differential equation, and this is 0 if and only if this whole term, that is the constant, is 0, because at any value of t this is either identically 0 or it is never 0. So the Wronskian value W of t is equal to 0 if c is equal to 0, and if c is non-zero, then W of t is never 0. Next, rather we can say the definition. Let x is equal to x1 of t, y is equal to y1 of t, and x is equal to x2 of t, y is equal to y1 of t be two solutions to the homogeneous system of linear differential equation 1, then the two solutions are said to be here 1 means this system of equation. Here what it means, 1, this is the system of equation. This is the system of equation named as 1, and if these are the solutions for the system of equation 1, linear differential equation, system of homogeneous linear differential equation, then the two solutions are said to be linearly dependent if there exists a real number, if there exists a real number k such that x1 of t is equal to k into x2 of t and y1 of t is equal to k into y2 of t or vice versa, and if there does not exist any k such that you can write this expression, then this is called as a linearly independent solutions. And if there does not exist any k, and if there does not exist any case such that this happens, then this system of equation is called as, then the solutions are called as a linearly independent. Now there is the relation between linearly dependence and the Wronskian. There is the relation between linearly independent solution and their Wronskian. Now if x is equal to x1 of t, y is equal to y1 of t, and x is equal to x2 of t, y is equal to y2 of t are two solutions of one, then two solutions are linearly dependent if and only if their Wronskian is identically 0 on the closed interval a b. If the Wronskian value of their solution is 0, then the solutions are called as a linearly dependent solutions. And the two solutions, these two solutions are linearly independent if and only if their Wronskian is never 0, or we can say that non-zero at least one point, because if the Wronskian is non-zero at least one point, then it is never 0. Okay, so if Wronskian is non-zero, solutions are linearly independent. If the Wronskian is 0, then the solutions are linearly dependent. So this is about the theory part. Now in the next lecture we will see about the general solution and particular solution to the system of linear equations, general solutions and particular solutions to the system of both homogeneous and non-homogeneous system of linear equations. Okay, in the next lecture we will see this point. Okay, thank you.